Hello, cosmic explorers, and welcome back to our channel. Look up, what do you see? During the day, it's that giant, blazing ball of light we call the sun. We see it every day, but how much do we really know about this celestial powerhouse that makes life on Earth possible? Today, we're embarking on an epic journey, 93 million miles away, to uncover the secrets of our very own star. From its fiery birth to its ultimate fate, and everything in between, we're going to explore the sun like never before. So grab your sunglasses, you're going to need them, as we dive deep into the heart of our solar system's king. Let's start at the beginning, shall we? About 4.6 billion years ago, in a vast, dark corner of the Milky Way, a giant cloud of gas and dust, called a solar nebula, began to collapse under its own gravity. Imagine a cosmic spinning top, getting faster and faster, pulling more and more material into its center. As it spun, the core grew hotter and denser. The pressure and temperature became so unimaginably intense that something miraculous happened. Nuclear fusion ignited. Hydrogen atoms started fusing together to form helium, releasing an incredible amount of energy in the process. And just like that, a star was born. Our sun flickered into existence, and the leftover dust and gas swirling around it eventually clumped together to form the planets, including our beautiful blue marble, Earth. So, what exactly is the sun made of? It's not a solid ball of fire like you might think. It's actually a gigantic sphere of super-hot, electrically charged gas called plasma. The vast majority of it, about 74%, is hydrogen, the fuel for its nuclear furnace. Another 24% is helium, the byproduct of that fusion. The remaining couple of percent is a mix of other elements like oxygen, carbon, iron, and neon. It might not sound like much, but that small percentage contains elements crucial for the formation of planets, and ultimately, life itself. Every second, the sun converts about 600 million tons of hydrogen into helium. It has been doing this for billions of years, and has enough fuel to keep going for about another 5 billion. That's a pretty reliable power source. Now let's take a tour of the sun's layers, starting from the inside out. At the very center is the core. This is the sun's engine room. It's incredibly dense, and temperatures here reach a scorching 27 million degrees Fahrenheit, or 15 million degrees Celsius. This is where all the nuclear fusion happens, generating all of the sun's energy. This energy, in the form of photons, or light particles, then begins its long journey outward. Surrounding the core is the radiative zone. Here, the energy from the core travels as electromagnetic radiation. But it's not a straight shot. The plasma is so dense that a single photon can take, on average, over 100,000 years to travel through this zone, constantly being absorbed and re-emitted by particles along the way. It's like a cosmic pinball machine. Next up is the convective zone. This is the outermost layer of the sun's interior. Here, the energy transport mechanism changes. Think of it like a pot of boiling water. Hot plasma from the bottom rises, cools as it reaches the surface, and then sinks back down again in a constant, churning motion. These massive convection cells are what carry the heat to the sun's visible surface. And that brings us to the surface, the part of the sun we can actually see. It's called the photosphere. Photo means light, so this is literally the sphere of light. It's what we perceive as the sun's disk. While it looks calm and uniform from Earth, it's actually a turbulent, bubbling sea of plasma, with a cool temperature of about 10,000 degrees Fahrenheit, or 5,500 degrees Celsius. This is also where we see sunspots, which are cooler, darker areas caused by intense magnetic activity. But the sun doesn't just end at its visible surface. It has an atmosphere too, with several distinct layers. Just above the photosphere is the chromosphere. It's a reddish layer that's usually invisible to us, but can be seen during a total solar eclipse as a faint red ring. Temperatures here actually start to rise again, reaching up to 36,000 degrees Fahrenheit. The outermost layer of the Sun's atmosphere is the magnificent corona. This is the wispy, pearly white crown you see stretching out into space during a total solar eclipse. And here's a real puzzle for scientists. The corona is mysteriously, mind-bogglingly hot, reaching temperatures of millions of degrees, far hotter than the surface below. We're still trying to figure out exactly why this is, but it's likely related to the Sun's complex magnetic field. The Sun's influence extends far beyond its visible atmosphere. It constantly breathes out a stream of charged particles known as the solar wind. This wind flows outward through the solar system at speeds of up to 1,000,000 miles per hour, creating a vast bubble around our solar system called the heliosphere. Earth has its own magnetic field, the magnetosphere, which acts as a shield, protecting us from the most harmful effects of this solar wind. When the solar wind interacts with our magnetosphere, it can create the beautiful auroras, the northern and southern lights. Sometimes the sun gets a bit more active. Its magnetic fields can get twisted and tangled, storing up immense amounts of energy. When this energy is suddenly released, it can result in solar flares, intense bursts of radiation, and coronal mass ejections, or CMEs, which are giant clouds of solar plasma hurled into space. If a powerful CME is aimed at Earth, it can disrupt our satellites, power grids, and communication systems. This is what we call space weather, and scientists are working hard to predict these events to protect our technology. So we know the Sun is our star, our source of light and heat. Without it, Earth would be a frozen, lifeless rock. The Sun's energy drives our weather and climate, powers photosynthesis in plants, the very foundation of our food chain, and even provides the vitamin D we need to stay healthy. From ancient civilizations who worshipped it as a god to modern scientists who study it with advanced telescopes, humanity has always been captivated by the sun. It's a constant in our lives, a daily reminder of our place in a vast and dynamic cosmos. What about the future? As we mentioned, the sun has about 5 billion years of fuel left. When the hydrogen in its core runs out, gravity will take over, and the core will start to shrink and heat up. This will cause the sun's outer layers to expand dramatically. It will swell into a red giant, becoming hundreds of times larger than it is now, likely engulfing Mercury, Venus, and possibly even Earth. Don't panic, though. This is billions of years away. After this red giant phase, the sun will shed its outer layers, creating a beautiful planetary nebula. All that will be left is its tiny, hot, and incredibly dense core, a white dwarf, which will slowly cool and fade over trillions of years. Studying the sun isn't just about understanding our own star. It's about understanding stars all across the universe. It's our closest stellar laboratory, allowing us to test our theories about astrophysics and the life cycles of stars. Every discovery we make about the sun helps us piece together the grand story of the cosmos. So the next time you feel the warmth of the sun on your skin, take a moment to appreciate this incredible cosmic powerhouse. It's a dynamic, complex, and awe-inspiring star that has nurtured our planet for billions of years and will continue to shape our future. It's the heart of our solar system, and we're lucky to be along for the ride. Thank you so much for joining me on this journey to the sun and back. I hope you've learned something new and feel a little more connected to our amazing star. If you enjoyed this video, please give it a thumbs up, and don't forget to subscribe and hit that notification bell so you don't miss our next cosmic adventure. Until next time, keep looking up.